Hello friends, in this video we will see about rank nullity theorem. Actually two famous result and two variation of the rank nullity theorem. Before that let me explain about you the extension of basis, which is I already done in my video. Okay, anyway let me recall. First of all, V is a finite dimensional vector space over a field F. Okay, finite dimension means the dimension which I already defined, it is n less than infinity. Okay, now what we are going to do, actually let A contained in V be a set, just a set, linearly independent set. Okay, maybe empty, doesn't matter. I am saying that it can be extended as a basis. How? Suppose A is spanning V, then linear independence plus spanning implies basis, right? In fact, that is the definition. So we are done. Otherwise, go to the span of A, suppose that is properly contained in V, then let V belongs to, let's say V1 belongs to V minus span of A. Now add V1 to this A. Now this is, let's say, A1. Okay, and this is going to be linearly independent, because we know that a set is linearly independent or there exists a vector which is previous linear combination of others. Since this is linearly independent, I cannot find a vector which is previous linear combination before that. So this is only can be written as previous linear combination if it is not linearly independent. But we have taken outside, see, outside V is here, span of A is here, we have taken here, so we can extend slowly. If it is, this is linear, this is linearly independent. Now this is spanning, if A was spanning in V, then we are done, this is a span. Okay, so we can extend A as a basis. Otherwise, go again, V minus A1, taken vector, if it is not spanning, then add into A1, let's call it A2, repeat the same process. Okay, so from there, because of finite dimensional vector space, we have to end this process. Okay, we will get into it. Okay, so what we are observing that any linearly independent set can be extended as basis. That means there exists a basis, it can be A itself, but such that A is a part of B, that basis. Okay, any linearly independent, this is what we need it. Okay, let's prove the first version of the rank nullity theorem. So many people don't call it rank nullity theorem, but it is a version of rank nullity theorem because of isomorphism theorem. Let V be a finite dimensional vector space, let W be a subspace, then dimension of V equal to dimension of W plus dimension of V, or dimension of V by W equal to, this is easy to understand. So we are, because of we are quotienting out, so it's easy to understand, dimension of V minus dimension of W. That many quotient is happening because we quotienting is kind of contracting or cutting it down. Okay, this is how it's happening. So let's prove this. This proof is easy. Really, you understand that there is a natural projection, let's call it pi V to W. Okay, and we have kernel of this nothing but W itself. This is very natural. Okay, a map any V equal to V plus capital W. This is how it works. I am sure that you know these concepts. Okay, the kernel of the map is W only. Okay, let W1 dot WK contained in W be a basis of W. Since there is a one thing I didn't do, but that is easy to understand. Every finite dimensional, suppose we have a finite dimensional vector space, suppose we have a subspace that is also finite dimensional vector space, that I didn't do. I think you know this is from basic, so I am concentrating on some other thing, so I don't really wanted to go into that. So you can ask why this is going to happen, because of that fact. Okay, fact every subspace of V is also, if V is finite dimensional vector space, also finite dimensional vector space. Okay, now let's extend this basis W1 up to Wk. We have seen that, let's say Vk plus 1 dot dot Vn. Extend this basis for V. Now this is basis for V. Okay, now what happens? Climb pi Vk plus 1 dot 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 pi Vn is basis for V by W. Suppose if I prove there are exactly n minus k elements. Okay, first I want to justify that. Okay, first of all, this is exactly n like this is like that. Okay, so you see that first of all, pi Vi not equal to pi Vj, when I not equal to j, I k plus 1 less than or equal to n and j. See why? If it is equal to, suppose pi Vj, if it is equal to, we have pi Vi minus Vj equal to I not equal to j. Okay, equal to 0. That means Vi minus Vj, let's say I less than j, equal to belongs to kernel of pi, that is nothing but W. That means Vi minus Vj can be written as summation alpha I into Wj's, let's say alpha I, let's say alpha k Wk's, k equal to 1 to k. Okay, I want to use some other notation. Let's say L, let's say L. Okay, so notation confusion. Okay, L equal to 1 to alpha L WL. See, we have W1 up to Wk, then Vk plus 1 up to Vm. Now Vi somewhere is, Vj somewhere is here, Vi somewhere is here. So that means Vj can be written as minus of, so minus sign will come ultimately. So that side minus Vi plus summation L equal to 1 to k, you see, alpha L WL. Sorry, not Wj, WL, here also WL. Okay, see, from here you can understand that Vi can be written as a previous linear combination of this, but that is not true. As I said in the lecture before, a set is either linearly independent or there is a vector, we can write it in a previous invariant. That is a shows that this is not linearly independent. This shows us this is linearly dependent because of this fact. Okay, in fact, what you can do actually, 0 equal to Vi minus Vj minus summation alpha L WL k L equal to 1 to k. Okay, so this is not 0, this is not 0, further this is 0 or not. So this is linearly combination, but not 0 coefficients are there, 1, because so we are contradicting the fact is A is linearly independent. Okay, because A is this. Okay, so slowly we can understand this set actually, Vk plus 1 dot 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 Vn is n minus k element. The cardinality is n minus k. This much is clear. Now let's see. Clearly this is spans. How? Let a vector V plus W belongs to V by W. Since alpha I Wi I equal to 1 to k, L equal to k plus 1 to n. Okay, beta L VL. V can be written as, because V belongs to capital V and A is the basis, so Wi's and V's are basis. So from here we can write like this. Now apply this thing, that is V plus W. That's how it works. But you remember that this we have taken out from kernel, so this entire thing will go to 0. So that implies pi L equal to 1, sorry, k plus 1 to n VL beta L. Okay, because of linearity, summation beta L equal to k plus 1 to n pi VL. So this is spanning. So every typical element here looks like this. This is spanning. So we are done. We are okay with that. Okay. So spanning is clear. Only I have to prove linear independent. Climb pi v k plus 1 dot 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 pi n is linearly independent. Let's see how to prove that. Okay, that means I have to take beta k plus 1 pi vk plus 1 dot plus dot 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 plus beta n pi vn equal to 0. I want to prove each scalar is 0. Now take the pi out because it's linearly. So beta k plus 1 vk plus 1 plus dot 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 plus beta n vn. This is because of linearity. This is 0. So this entire thing belongs to the kernel. So beta k plus 1 vk plus 1 plus dot 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 plus beta n vn belongs to kernel of phi, but that is nothing but w. This much we know. So that means this summation L equal to 1, sorry, k plus 1 to n beta L VL equal to summation, because we know that Wi's are spanning, Wi I equal to 1 to k alpha i's. This is happening. So let's write it clearly. Summation alpha I Wi I equal to 1 to k minus summation L equal to k plus 1. If I made a mistake like in the index, please correct it. Okay, so indexes are very important. Beta L VL equal to 0. I am rewriting the statement here, but we know that Wi's along with VL's forms linearly independent set. So this is 0 implies each alpha equal to 0 and beta L's are 0 for all I, but I doesn't matter for us. This is matters, L is matters, beta L's are 0, which is I wanted to prove. So exactly I wanted to prove. So this is linearly independent. So that implies dimension of V by W equal to dimension of V minus dimension of W, because that is nothing but n minus k. This is what I want to prove. Okay. So the corollary, that is a actual rank nullity theorem corollary. Before the corollary, we know this fact, which is I am taking granted. You can read it. Suppose we have a linear transformation from V to W. Both are this is not necessarily finite dimensional, but we want V is finite dimensional. Okay, V by kernel of T isomorphic to image T of V image. This is called the first isomorphism theorem. So from here you can understand that the rank nullity theorem clearly this is the version we wanted to enforce. Okay, corollary. Let there is a linear transformation V by W, then dimension of V equal to dimension of kernel, which is called nullity, plus dimension of range TV. So this is called nullity, this is called rank, the dimension of the range is called rank, and this is called nullity. Okay, so proof is almost trivial from that, because V by kernel of T isomorphic to the V, we know that from first time. So this is dimension of V from last dimension of 3 dimension of kernel of T equal to dimension of TV. From the last theorem we know, so dimension of V equal to dimension of kernel of T, the nullity, plus dimension of TV, the rank. That's all. This is what I want to prove. Okay, there is one more corollary from this which is very very important corollary, and I want to make one definition that is also very important. Okay, let phi from V to W be a linear transformation. Okay, and dimension of V equal to dimension of W, both dimension of same, then the following are equivalent. This symbol I explained, this is a TFAV, the following are equivalent. Okay, I explained already in previous lectures. You have to use my previous lectures to understand these lectures also. Okay, 1, phi is an isomorphism, that means 1 to 1 onto 2, phi is 1 1, 3, phi is onto 4, phi sends basis to basis. Okay, we will see how to prove this. Okay, and the proof is clear, very easy. We will prove 1 implies 2. So phi is isomorphism. Yeah, phi is isomorphism implies phi is 1 to 1, so that's clear. 2 implies 3, because isomorphism definition involves 1 to 1 and injective and surjective, 1 to 1 and 2. Okay, 1 implies 3 also clear, but anyway 2 implies 3. We will see. Phi is 1 to 1. 1 to 1 means kernel is trivial, so dimension of V equal to, by rank nullity theorem, dimension of kernel of phi plus dimension of the range TV, the dimension of the range, but this is 0 because of T is 1 to 1, kernel is trivial, right? So this is 0, so dimension of V equal to dimension of TV, but that is nothing but dimension of W, because see, the dimension are same, so this must be onto, because both dimensions same. This TV is a proper, the capital V. Okay, proper subspace of W. So 2 implies 3 is clear. Now 3 implies 1. Let's see, since onto this, like I want to say that this sense to sense, basis to basis, let v1 dot 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 vn be a basis in V. So tv1 dot dot vn, sorry, phi, I used phi vn, claim this is basis. Okay, this is basis because we have onto. The onto condition says that it's like, okay, the onto condition. Before that I wanted to do like okay, see, this is like, okay, anyway, this is onto the on, because of onto V, every W belongs to W, there exists V belongs to V, such that phi V equal to W. This is onto. So phi summation alpha I Vi, because every V can be written as this, so summation alpha I phi Vi, that is nothing but so this is W, so that means every W can be span, every W can span. Okay, also this is because of onto, so that means v1 dot dot phi vn spans, and we know that this is as spanning linearly independent set less than or equal to spanning set, we know. So the dimension of W equal to dimension of V, this is spanning, so this phi v1 dot 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 phi vn must be less than or greater than, because n greater than or equal to n, but see, we have given n elements, it can be goes less than or equal to n, because it is a function goes from n element set to the other set. It can go at most n or lesser than that. Okay, v1 vn goes to phi v1 phi vn. It can go at most n or less than that. This is just a function, right? Because after all, so from here it's understandable that this is like spanning as exactly having n elements. So minimal spanning set, hence it is a basis. You have to see my characterization of basis. The 4 characterizations given: basis, maximal linearly independent set, minimal spanning set, and every vector can be written as unique linear combination. That clearly explained that I am using. See, this is a very important minimal spanning set. So from here we can conclude that this is basis. Okay, 4 goes to 1 is very simple. Okay, see, in this fact we okay, anyway, 4 goes to 1 is very simple. Send basis to basis. So spanning is clear. We want to claim that phi is isomorphism. Phi sends basis to basis. So spanning is clear. So the range of V is W because of basis to basis. And only thing we wanted to show that this is 1 to 1. Okay, let's show 1 to 1. Phi of V, suppose 0 for V belongs to V. I want to show that this is equal to this. Okay, let's take a 1 to n. We are spanning set. So V can be written as for V can be written as alpha I Vi. Okay, so phi V, that is equal to 0, that is equal to summation alpha I phi Vi, because basis goes to basis. This is basis, this phi Vi is or basis linear combination. Once you get 0 for basis linear combination, what happens? This alpha is or 0, that implies V equal to summation alpha is Vi, so that is equal to 0. So 0 goes to 0 and 0 only goes to 0, so hence is injective. So this is isomorphism. So finally the summarization is this. These are the isomorphism if any one condition met. Okay, and the definition I am making the non-singularity. Okay, the definition. Okay, let me get it. Phi goes to V to W be linear transformation of vector spaces. The kernel of phi is called null space. Okay, the image or range of phi is called range space. Okay, or so the dimension is called rank. The kernel of phi equal to the dimension of the kernel, I mean the nullity equal to 0 implies, I mean we call phi is singular, sorry, non-singular. Okay, because we can really define the inverse to the restricted space. Okay, we want finite dimensional here. Okay, so far, but many definitions, so you can go for infinite dimensional. Okay, fine. In the next video I will post some important example from Demet and Ford, which is peculiar little bit, but it is very needed for exam point of view. Thank you.